All right, so in this chapter, what we want to do is describe motion. Okay, so if an object is moving, then we want to describe that motion. And we'll see what that means. Okay, so for instance, now I got to record this, so if it was just a class, I could hand wave and stuff, but I can't now. All right, so let's say this is a coordinate system, and let's say you go flying. Okay, we want to describe this motion. Okay, how would you describe this motion? Anybody want to attempt that? All right, so that's slightly complicated. So let me show you another easier motion that maybe you can describe. Okay. So let's say this is you in the car and you're driving. Okay, and this is a couple of pictures showing you your location. Okay, you guys want to describe that motion now?
Linear.
Yeah, so that was the simpler part. So we restricted you to move in one dimension. All right.
Accelerating forward.
Oh, I'm sorry?
Accelerating forward.
How do you know it's accelerating?
Well, because it's since that's like a stock camera, it's moving from one point to the other. So depending on like the interval of the stop camera, you could tell like how fast it's moving.
Okay. So you see, describing in words can be a problem, and that's not a very precise definition. Okay, and if I ask you what is the acceleration at any given instant, you can't. Okay, so a more detailed way would be, you could mark what time this is at that location and so on. Okay, and that's what this is. Okay, so we can agree that we can say that, let's call this the x-axis. There is the origin. This is the positive direction. There is the negative direction. Okay, so here is the x position. Your location is with reference to this coordinate system. There's your position, and these are the times at which it is. Okay, so this graph is a complete description of the motion. Okay, so for instance, here at 10 seconds you were there. At 10 seconds you were at 50 meters. At 20 seconds you were at 38 meters. At 25 seconds you were in 20 meters, and so on. Okay, so this graph is a complete description of the motion. Okay, so now when we say we want to describe motion, what is the most useful description? You can try and describe it in motion. You are moving to the right of this, that, and the other. All that leads to is very imprecise. This is what we want. Okay? We want your location as a function of time. That is a description of motion. Okay? And once you have that, okay, so I'll just give you the punchline now. Okay, so we'll, and how many different kinds of motions are there? I'm sorry? I'm sorry?
Oh, I didn't say anything.
Okay. Well, I want you to say something. How many different kinds of motions? There's an infinite. How many functions can you think of? Infinitely many. There's infinitely many. Okay, so here's a simple one. Okay, there's a function. Okay. Now, this motion, this contains all the information there is about the motion. You can calculate anything from this function, from this description. Okay, so one of the things we'll be interested in is what's your velocity at any given time. Okay, and you will learn in this chapter, so the velocity at any given time is time derivative of your position. Okay. Have you guys taken derivatives?
Yes.
Okay. All right. So I have trouble with them. So can somebody help me out?
15t squared.
I'm sorry?
15t squared.
Mm-hmm.
14t plus 8.
14t plus 8. Okay. All right. So notice this. If this is a polynomial, the velocity is a polynomial of degree 1 less. Okay. All right. And given the velocity, I can calculate the acceleration at any time. Okay. And you will learn acceleration is dv by dt, which is, okay, the second time derivative of position with respect to time. Okay. All right. Who's got this?
30t
30t
plus 14.
14. Okay, and generally this is all we're interested in, the velocity and acceleration. Okay. Okay, if you take the time derivative of acceleration, if you need this, then you're pretty good. Okay, and this thing is actually called a jerk. Okay. So, you know, when you're interested in rate of change of acceleration, you're dealing with rockets and stuff like that. Okay. All right, so that's the punchline. Okay, so this chapter is about, okay, we want to describe motion. When we are saying we want to describe motion, what we are looking for really is your position as a function of time. And once you have this function, then you can calculate everything. Okay, your velocity at any given time is dx by dt, and your acceleration at any given time is dv by dt. I'm sorry?
You mentioned
Uh,
dA.
Oh, that, okay, you can keep taking time derivatives. How long can you keep taking time derivatives? Forever. Okay. This happens to be useful in some circumstances, and it's called a jerk. Okay. All right. So that's the deal. Okay. Now, in this chapter, we'll keep it simple. We'll deal with one-dimensional motion, but this can be easily generalized. Okay. What does describing a motion mean? Giving a position as a function of time. So let me tell you what you're going to encounter in the next chapter. Okay? In the next chapter, you're going to encounter 2- and 3-dimensional motion. X, Z. Okay. So let's say you are here. You're in a plane, and you are there. Okay. This is your position vector, R. Everybody understand that R can be written as xi plus yj plus zk. Right? Everybody understand that? Okay. Okay, we will draw that. So there is a projection of R on the xy plane. Yeah. There's your x coordinate, and there's your y coordinate, and there's your z coordinate. All right, what if this were a plane and this was moving? So what if you were in a plane and this was moving? You wanted to describe this motion? What you're really asking for is this guy. How is your x, y, and z coordinate changing with time? Okay. All right. So there's a description of motion in 3 dimensions. Okay. What is the velocity? So again, remember this is coming in the next chapter, but you're already good enough to understand this. You take the derivative of 3 functions. So this is, take the derivative of that function. So dx by dt I. So what is this? This is the x component of the velocity. Yep. What term is next? I'm sorry? Very good. dy by dt j plus
dz over dt k.
very good. All right, there you go. You have three-dimensional motion. If you wanted the acceleration, who can help me out with what is acceleration? I'm sorry? And you take derivative once again. Okay. All right, so now let me tell you why we're doing one-dimensional motion. Okay. So it turns out that if you're going in, let's say you're flying like this, okay, and if you apply, so this motion, there's the projection of the motion along the x-axis, there's the projection of the motion along the y-axis, there's the projection of the motion of along the z-axis. Okay, you guys understand that? Okay. Now, if you have a rocket that's pushing you in this direction, will it affect the motion in the y and z direction? No, it doesn't. Okay, so you can describe the motion along individual axes independently. Okay, so rather than starting off trying to describe a three-dimensional motion with, remember, you eat a steak one bite at a time. So we will just describe one-dimensional motion, and then you can put together as many dimensions as you want. Okay, and that's the idea. Did you guys understand that? Okay. All right. Now, so I drew this plane, I drew your jet flying like this. Okay. Now, drew your jet as a point particle. Is your jet a point particle? Okay, so now I guess the recording people will have to deal with this, but here's your jet. If it's doing a barrel roll and stuff like that, then you can't describe this as a point particle. Okay. If it's flying such that every point on the jet has the same velocity and same acceleration, then you can treat it as a point particle. Okay. So now you can't, so what we're going to do is we're not going to add rotational motion to our motion. Okay. We're always going to treat all our objects as point particles for now. Okay. So what that means is every point on the object has the same velocity and the same acceleration. Okay. All right. All right, so, well, I mean, you already know the 2 chapters now, so I'll just quickly go over the slides. Okay. Again, do you guys understand where we're headed? Okay. So what is it that we're trying to do? We're trying to describe motion. And when we are describing motion, what do we mean when somebody says describe a motion? I'm sorry? No. Give the position as a function of time, right? That's, all right. So describing a motion, it means giving position as a function of time, okay? So we'll consider 1D motion in one dimension initially, okay? So it has to be a motion in a straight line, okay? Forces can cause change in motion. What does that mean? Forces can cause change in velocity is what we really mean, okay? And so and Newton's laws will tell us that F equal to ma is what that equation is, okay? And we'll talk about that later, okay? We consider motion of particles, that is point objects, or objects that move like a particle. That means every part of the object has identical motion, okay? So it's not spinning. If an object is spinning, then different points have different velocities. Okay? All right. Okay, so describing this motion, the most useful form for us is giving the position as a function of time. But you also know that once you have that, you can also give it as and draw it as a graph. Okay, but again, this is the most useful form for us. Okay. We already talked about vectors and scalars. There are quantities in physics that we study that are represented by vectors. Velocity, acceleration, displacement, these are all vectors. Forces, momenta. Okay. And there are other quantities that are scalars, speed, pressure, etc. are scalars. Okay, so to specify these guys, you need more than one number. To specify these guys, you just need one number. Okay. How many numbers do you need to specify velocity? I'm sorry? It depends on the number of dimensions you are in. So in 3, you need 3 numbers.
And in n, you mean n.
Very good. No, n numbers. N minus 1 for the number for the directions. Okay. All right. You guys understand that? Okay, so in 3 dimensions, you need 2 numbers to specify the direction. Okay. So for instance, if your velocity is like that, you need this angle, okay, and this angle. So you need 2 numbers to specify the direction of the vector. Okay. So anyway, there are physical quantities that are represented by vectors, and there are other quantities that are scalars. All right, so in 3 dimensions, to specify a vector, in 3D, to specify a vector, you need 3 numbers. 1 number for magnitude, and 2 numbers for direction. Okay, in 1 dimension, to specify vectors, how many numbers do you need? So how do you tell the difference between a vector and a scalar?
Scale,
We have a quandary, right?
scale only needs one number.
She just said 1 number for a vector too. All right, so 1 dimension is a kind of a special case. Okay, so here's 1 dimension, but here's something. So let's talk about you driving on I-95. Well, you can either go north or south. Okay, so this is plus 5 meters per second, and this is minus 4 meters per second. So the sign gives you the direction. Okay, it's not a number. The sign tells you the direction. Okay. All right. So position is location of a particle with respect to a coordinate system. Okay, so when you say you're located at 5 meters, what does that mean? 5 meters with reference to what? Okay, 5 meters with reference to, and you're located at 50 miles north on I-95 with reference to Daytona Beach or with reference to Miami and so on. Okay, so position is a location of the particle with reference to a coordinate system. Okay, a description of a motion can be given in terms of a position versus time graph, or mathematically given by position as a function of time. Okay, so in 1D, this is what we are interested in. In 3D, this is what we are interested in. Okay, so to describe motion in 3 dimensions, what I need is for you to give me 3 functions in time, 3 functions of time. Okay? So if I wanted you to give me motion in n dimensions, I'm asking you for n functions of time. Okay? All right. You guys following this? All right. So now we're defining quantities. So we've defined position. Position is your position with reference to some coordinate system. With reference to some coordinate system. Okay? Now we'll define something called the displacement vector. This is a vector. Okay? And okay, so we'll come to the to 1 dimension in a second, but let's do the easier case, the 3-dimensional case to picture. Okay, so let's say you went on a flight. This is your position at T1, and this is your position at T2. Okay, so there's your position vector at T1, R1, and there's your position vector at T2. Do you guys understand that? What is the displacement vector? It's from your initial position to your final position. That is your displacement vector. And it is written as delta R, which is always the final vector, final position, which in this case is R2, or let me change that. We'll call this our initial time, final time, final time. R final minus R initial. Okay? So the displacement vector is a vector from your pointing from your initial position to your final position. Okay? Now, the displacement vector is sort of a very average quantity. Okay, so let me show you. Okay, what's your displacement vector? I'm sorry? 0 vector. Okay. What is the displacement vector now? 0 vector. What is the displacement vector? This guy, right? What is the displacement vector? Same vector. Okay, so you see infinitely different paths can have the same displacement vector. Okay, so the displacement vector doesn't give you any details of your journey. Okay, so it's a very gross statement of, well, it is useful. I mean, for instance, you could have gone around the world from starting from here and ended up in New York. It tells you where you ended up. Okay, all right. But it doesn't tell you details of your journey. Okay, so here is 1-dimensional motion, and so to graphically represent it, you have to have it. You have to show how time evolves. So what this means is, you initially went in that direction and then walked back in this direction. And so if this was your endpoint, you see your displacement vector is 0. Okay. For this journey, your displacement vector is that guy. Okay. And what is your displacement for that journey? So that was 1 kilometers and 1 point. So it is minus 7.75 kilometers. Okay. So the displacement there, delta x, is minus 0.75 kilometers. Okay. Again, as we said, the negative sign tells you the direction, and the magnitude tells you the magnitude of the vector. Okay. All right, anyway, so the displacement is a vector. This guy is a vector, even though we haven't written an arrow on top. It's the final position minus the initial position. Okay. In 3 dimensions, it's better. The displacement vector is final position minus the initial position. Okay, that's the same thing here. Distance is a scalar. Again, now don't get hung up on a lot of the terminology. You'll get it all. Okay, so as long as you know how to take derivatives, you'll be good. Okay. This guy is a vector. This guy is a scalar. Okay. Now for this journey, the displacement vector is 0 vector. The distance traveled is 1 kilometers. Okay. For this journey, the displacement vector is negative 0.75 kilometers. The distance traveled is 2.75 kilometers. Okay. Okay, so for these two journeys, the displacement vector is the same, negative 0.75 kilometers. The distance traveled is very different, okay? 2.75 kilometers and 6.75 kilometers. Okay. All right, so distance is a scalar. Again, don't worry about a lot of this stuff. I think they should teach 3 dimensions right off. 1 dimension is a little confusing. All right. Average velocity. What kind of quantity is this velocity? Is it a vector or a scalar? It's a vector. Okay? And so let's look at the equation. So here's the velocity. Here's the equation defining velocity. It's displacement. That's a vector. How about time? Is time a scalar or a vector? Scalar. Okay. So, and you guys know that if A is a vector, you multiply it by 1/3, what did you get? A vector. So you multiply or divide a vector by a scalar, you get a vector. So this is a vector. Okay. So the average velocity is displacement divided by time. Okay. All right, so let's say you go to school and come back home. You came back home 3 hours later. What was your average velocity? I'm sorry? So average velocity is displacement over time. Displacement was 0, so it's 0 vector. You came back 5 hours later. What was the average velocity? 0. So averages are, they give you some information, but no details at all. Okay. All right. Units. What are units? This thing is measured. SI units are meters, seconds. So meters per second. Average speed. Speed is a scalar. Okay. Speed is distance divided by time. Okay. So that's a scalar divided by a scalar is a scalar. Okay. And now, okay. So for this guy, you can calculate the average speed, and you can calculate the average speed for this guy. Will there be 0? No. Speed won't be 0, even though the velocity is 0. So you can see that velocity, average velocity and average speed are not related. Okay. We'll define instantaneous velocity and instantaneous speed, and those will be related. Okay. Instantaneous speed is the speed that you read on your speedometer when you're driving. Okay. And that will be the magnitude of the velocity. Okay. So average speed and average velocity are not related. Okay, so now this is what you want to make sure you understand. Instantaneous velocity, what does that mean?
Slope at the tangent line.
Well, very good. Instantaneous velocity means what is your velocity at this instant? Okay? And instantaneous velocity, so here's the expression for the average velocity. And so instantaneous velocity just means that you take this interval dt going to 0. And this was the derivative. Okay? And that's what our friend just said. You learned in your calculus classes, if you draw x as a function of time, which was the description of motion, dx by dt is equal to slope of the tangent line. Okay. So if it's position versus time position versus time is what you plotted, this slope is velocity. And you'll see in the next slides, if you plot velocity versus time, this slope dv by dt will be acceleration. Okay? All right. All right, so the velocity is dx by dt. This is instantaneous velocity, okay? And magnitude of the instantaneous velocity is instantaneous speed, okay? So those two are related. Yeah. Is everybody comfortable with taking derivatives? All right. You haven't done derivatives? Okay. So here's a 10-second lesson on derivatives. Okay. You've done functions. You know functions. All right. And there's a video on YouTube channel as well, so you can look at it. So one of the things we are interested in a function is how fast it's changing. Okay. What's happening to the function here? As you move forward, it's decreasing. Here it's increasing. It's increasing less fast. Here it's increasing much faster, right?
Yeah.
Okay. So how can you convey that quantitatively? The easiest way is draw a tangent line at this point and ask for the slope of the tangent line. That tells you how fast it's growing or decreasing at that point.
Okay.
Okay? And that slope is df by dx. Okay? And then you get, so if fx, so, okay, x square, what is the derivative of x square? 2x. Okay, do you understand?
Yeah.
What is the derivative of x to the power n?
And b n times x.
Again, n x to the power n minus 1.
Okay.
Okay? Derivative of ex, here's a very special function.
E to x.
Huh?
E to x.
Very good. That's the only function whose derivative is itself. Yeah. Log x, 1 over x, sine x,
Negative 6.
All right, so you guys are all experts now. Yeah. All right. When are you accelerating?
When your speed's increasing.
When your velocity changes. Okay? Whenever your velocity changes, you're accelerating. Okay, so So, people have trouble with this, so and people have trouble with this 8 chapters from now, so we'll do it right now. Yeah. If you start off by learning to run, will you have trouble walking? No. Right, that's the idea. No, I mean, I just want to make sure you understand, okay? Okay, so let's say we drive around in circles, okay? And we're going to drive around at 50 miles per hour. Hmm? Are you accelerating? Hmm?
No.
Everybody agree? No. All right, what is velocity? Velocity is a,
Displacement over time.
I'm sorry?
Displacement over time.
No, velocity is a vector or a scalar?
Oh.
Vector. What does a vector have?
Magnitude.
Magnitude and direction, okay? So let's say 50 miles an hour, that's the magnitude. 50 miles an hour, that didn't change. Did the direction change?
Yeah.
Velocity changed. If velocity changed, you must be accelerating. You are accelerating. Okay, so in this case, only the direction changed. Okay? And like I said, in 6 chapters, you'll learn when only the magnitude changes, your acceleration is perpendicular to the direction of your velocity. Okay? And the acceleration will point towards the center of the circle. And so it's called centripetal acceleration.
That's orbiting.
What's that?
That's orbiting.
Very good. So, you couldn't orbit unless there was a force acting on you. If there was no force acting on you, you would just go straight. If there was no sun, the earth would just go straight. Okay? All right, so we'll keep it simple. Well, we'll say, when are you accelerating? Whenever velocity changes, you're accelerating. Okay. How can velocity change? It can change, so magnitude of the velocity can change. So now I'll give you that example. So you're driving on 95 and there's 50 miles per hour, 60 miles per hour, 70 miles per hour. Okay? So here, in this example, only the magnitude was changing. Okay? And when only the magnitude changes, it turns out that the acceleration is tangent to the path. Okay? And when only the direction changes, the acceleration is perpendicular to the path. Okay? And of course, you can have a combination of both. But those are the 2 extreme cases. Okay? So again, when do you have acceleration? Whenever velocity changes with time. Okay? So whenever velocity is a function of time, then you're accelerating. Okay? So if any of those guys, if those guys are constant, then you're not accelerating. Okay? All right. Go ahead.
No, I'm good. I actually need the next one.
I'm sorry? Okay. Okay, so this is, again, when is your acceleration tangent to the path? Do you guys understand that statement? When is acceleration tangent to the path? Very good. Say it out loud. Very good. When is acceleration perpendicular to the path?
Direction changes.
when only the direction changes, okay? Okay. All right, so when are you accelerating? Whenever your velocity changes. And here's the formula. See, acceleration is dv by dt. It says it right in the formula. If the velocity is not changing with time, this acceleration would be zero. Okay? So we're just, I spoke for 20 minutes till all you guys got blue in the face, but all that is expressed mathematically in one simple statement. Okay? See, A is dv by dt. When is this not zero? When this is not zero. When is this not zero? When velocity depends on time. Okay? So as long as velocity depends on time, it's changing with time, and so you have acceleration. Okay? Okay, have you guys, do you know the fundamental theorem of calculus? Very good. How about you, my friend?
Not me.
Not you. You're in Calc 1?
Yes.
Okay. What calc are you in? 2. 2. 2. All right. They don't know what they're doing. You're doing good, okay? Don't worry about it. So here's,
Appreciate it.
yeah. Don't worry about it. Just buy me coffee later, okay? All right, so here's the fundamental theorem of calculus. Okay. Have you done integrals? No, not yet. Don't worry about it. Okay. Well, you've done derivatives, so this is all that the fundamental theorem of calculus says. Okay, so if all right, we'll go back one step. Okay, so this is just keeping it very simple. Even I understand this. This is a function, right?
Mm-hmm.
So one of the things we are interested in is how fast the function is changing. Okay, at this location, is it increasing or decreasing? At this location, what is happening? It's decreasing. At this location, it's not changing and all that. And how is that conveyed?
The slope.
Very good. The derivative tells you, the slope tells you if the function is increasing or decreasing. Another thing we are interested generally is what is the area under this curve. So that's the second fact we're interested in. Yep.
And that's where integrals come in.
Very good. See, you're a lot better than you give yourself credit. And here, see, this is that. Okay, that's the area. All right. All right, so now you understand that?
Yeah.
Okay. All right, so here's an integral. I mean, this is also a function, right? If this function is a derivative of some other function, you take the integral, the fundamental theorem of calculus, all it tells you is you evaluate this function at the two endpoints. That's
Points like on two different.
on the limit, this, okay? So it's like this, x1 and x2, okay? So this area, as long as this guy is this function, what you plotted is df by dx, okay? If that's what you plotted, this area is equal to the function f evaluated at x2 minus function f evaluated at x1.
Okay.
Yeah, that's a fundamental theorem of calculus. You guys understand? My friend, you have a quizzical look on your face.
No, I think I got it.
All right. All right. So we are going to use that. Yeah. I'm just going to do it for one thing. It's and then I'm going to go over the important formulas that we will be using for solving problems. Okay. We already know this. Everybody agree that velocity is dx by dt. Okay. So here's an equation. Okay. Now the beautiful thing about mathematics is all right, I've not drawn arrows on top to indicate vectors, but that's because you all understand that. Now, the beautiful thing about an equation is if you hit this guy with a hammer, what do you have to do?
And the other one with the hammer itself.
Very good. Hit the other guy with a hammer. All right, this is the hammer we're going to hit it with. We're going to apply the fundamental theorem of calculus to that one. xt2 minus xt1. What is this guy?
There.
I'm sorry?
Is it the area?
That's the displacement. So the displacement is your position at the final time minus position at the initial time. That's the displacement vector. And that is equal to, and what is this guy? That's the area under that curve. So if you plot velocity versus time, the area under that curve is the displacement vector. Okay? All right, that's the meaning. Again, this is, you just need to be aware of it, okay? Similarly, if you plot acceleration versus time, the area under that curve will be the change in velocity. Okay? All right. Don't worry about it. Take your time at home and you can look at it. But I want just make sure you understand all how to solve all the problems. Okay, as long as you're good with taking derivatives, you'll be good in this chapter. Okay, and you won't even need to take derivatives for most of the problems. Okay, so the area under the acceleration versus time graph is the change in velocity. Okay. All right, this I want you to understand. Okay. What is this graph, this picture telling you?
Which side they go?
I'm sorry?
Which side they go?
Right. So can you tell me more? Very good, my friend. See, this is the red arrows are the velocity, and the velocity vector, the magnitude or the direction is not changing. So the velocity is constant. What is the acceleration? 0. Very good. Okay, so when the velocity is constant, acceleration is 0. Okay, let's look at this picture. What is happening to the velocity? The magnitude is increasing. Only the magnitude is changing. And so the acceleration was tangent to the path. I'm sorry?
The acceleration has to increase as well.
Ex-
With at least that one.
No, here here it's showing constant acceleration.
Okay.
Okay. Here the magnitude was decreasing, and so the acceleration is pointing in the opposite direction. Okay. So when acceleration points in the same direction as your velocity, your speed increases. When the acceleration points in the opposite direction as your velocity, your speed decreases. Okay. Right now, we are considering situations where only the magnitude of the velocity is changing. We're not considering directions changing. Okay. We'll consider that next chapter. Okay, something is bothering you.
No.
Go ahead. You've already paid your money.
No, it's okay. It's
We've
okay.
already taken your money.
You're good. You're good.
We are happy.
I was gonna say, yeah.
This is the only business where we take your money first in. All right. So velocity and acceleration are related. Okay. Acceleration is non-zero when? When is acceleration non-zero? Go ahead. When velocity is changing. Okay, so here velocity. Okay, so you're accelerating because velocity is changing. Here velocity is changing. Again, all these are with respect to time. So you're accelerating. Here velocity is changing. You have acceleration. Here velocity is not changing. So acceleration is zero. Okay. So this guy, here the rate of change of velocity is constant. Acceleration is dv by dt. dv by dt is the slope of the tangent line. And you see the slope of the line is not changing. So acceleration is constant. It's that. And here the acceleration is zero. Slope is zero there. Okay. So this graph corresponds to that. Here, again, the slope is not changing. This acceleration is constant. This corresponds to that. Okay. Here, the slope of the tangent line is increasing. This graph corresponds to it. All right. Now, for the amount of money you paid for this class, all we're going to do is consider this kind of motion. Constant accelerated motion. Okay? That's all we're considering. And this is the only example that you see in sort of real life. A freely falling object. This guy has constant acceleration. Okay? And that too, he doesn't have that much constant acceleration for very long. So if you go across the tallest building on campus that's across the street, 5-story high, you drop this from the roof, it'll hit the ground in 2 seconds. Okay, so it maintains constant acceleration for that time. Okay. Maintaining constant acceleration for a long time is very hard. Okay? But that's all we'll consider. Okay, so you saw that when acceleration is constant, okay, velocity is linearly increasing with time. Okay. All right, so let me show an example. Okay, so now let me also tell you another thing while we're at it. Now, a lot of times I don't write units just because it gets messy. All right, so here is position, the SI units for position. We're measuring distances from the origin in meters. Okay. What are the units for this guy? I'm sorry? Okay, no, for this whole term. Meters. No. For this whole term, it has to be in meters. This is in meters. This is in meters. What you're confusing is the following. This term has to be in meters per second square because this term is second square, and that'll cancel with that. What are the units for this term? Meters per second. Okay? And that is second, it'll cancel that. So you see this guy, this 5 has units of acceleration. This guy has units of velocity. And this guy has units of distance. That's in meters. Okay? So you have to be aware of that. Yeah. Did you guys understand that? Okay. I saw maybe. All right, everybody understand that? Okay. All right, so now what we're going to show, so, all right. So what is the velocity? Okay. So again, the units would be meters per second square. All right, so what we are going to consider is mostly motion where acceleration is constant. Okay. So when acceleration is constant, velocity is a linear function of time. Position is a quadratic function of time. So this will be a parabola, this will be a straight line, and this will be a constant, okay, a horizontal line. So that's the motion, that's the kind of motion we'll consider mostly. Okay? Did you guys understand that? All right. So we'll consider motion where the acceleration is constant, velocity is linearly increasing with time or decreasing with time. Okay. The position is a parabola with respect to time. Okay. Is a quadratic function of time. Okay. So when the acceleration is constant, it turns out that, so these are the four kinematic equations. Okay, remember what we are interested in is description of motion. Okay. So what this equation is telling you, x minus, and this is shorthand, at x at 0 time equal to velocity at 0 time times t plus 1/2 acceleration times time squared. So what this is telling you is this is your position at time t, and that's written as just x. This is your position at time 0. That is your initial position, and that's written as x sub naught equal to velocity at time 0. Okay, that's written as v naught t plus 1/2 a t squared. So this is giving you displacement as a function of time, or you can also think of it as a position as a function of time. And you see, I told you that it's a quadratic function of time. Okay. So again, and when the acceleration is constant, the displacement is average velocity times time, and when acceleration is constant, average velocity can be written as final velocity plus initial velocity divided by 2. Okay, so that's the only time where you can do that. Okay, so when acceleration is constant, average velocity is final velocity plus initial velocity divided by 2. Okay. What is this telling you? This is telling you velocity at time t equal to velocity at time 0 plus acceleration times time. So this is giving you velocity as a function of time, and you see it's a linear function of time. Okay, when is that true? Only when acceleration is constant. Okay. What is this giving you? What's this equation telling you? It's telling you your velocity at a given position. So this formula is giving you your velocity as a function of position. Okay. Again, so we will mostly use these three equations, this one and these two. Okay. For most of the problems we solve. All right, so again, this is motion where the acceleration is constant. Okay. So this thing goes through the derivation. Okay, for constant acceleration, it's deriving these things. I'll just show you how to do this one case. Okay, and again, you don't have to remember any of this. Okay. So let's go. Acceleration is dv by dt. All right, so we are going to say acceleration is constant. Okay. So here's your equation, and we're going to hit both sides with a hammer. and this is the hammer we're going to hit with. Okay. We'll call it T1. Okay, everybody agree with that? Okay, acceleration is constant, meaning it's not a function of time, so we'll pull that out. Okay, and so that is dt. And this from the fundamental theorem of calculus is velocity at t1 minus velocity at 0. Okay. Well, this is the integral of that is just t 0 to t1. Okay, so a t1 minus 0 equal to v t1 v0. We'll write, this is t1, so we'll write this as, now we'll write t1 equal to t, at is v at t minus v0. Okay, so that's the shorthand notation. Okay, okay, well, I'll write this v at t. Okay, so vt, velocity at time t, is equal to velocity at time 0 plus acceleration times time. Okay, so velocity is a linear function of time. Okay, again, you don't have to remember any of this derivation. So for constant acceleration, this is what velocity is, v naught plus at, x minus x naught, displacement is v naught t plus 1/2 at squared. Okay, so these are just derivations of these formulae. Okay. And like I said, a freely falling object is one place where you encounter constant acceleration. So you can take your keychain and drop it until it hits something. The acceleration is constant. Okay. So a freely falling object is any object moving under the influence of gravity alone. That is, air drag is negligible in this motion. Okay. So for instance, can you rip a piece of paper, my friend? Okay. All right, so I'm going to drop this keychain and this thing, okay, without falling down. Yeah. This was freely falling. How about this guy? Was that freely falling?
Yes.
Was its acceleration 9.8 meters per second? No, so in this case, air drag was not negligible. This was not freely falling. Okay, do you guys understand the difference? Okay, this was freely falling. All right. So when you drop an object from rest, so these are at time t equal to 1 second, it'll have, the acceleration is pointing downward. The magnitude of the acceleration is 9.8 meters per second squared. Okay. So let's say I toss a ball up. Which way is the acceleration pointing? When the ball is going upward, which way is the acceleration pointing? I'm sorry, downwards. Okay, the acceleration is always pointing down. Okay, and its magnitude is the same. All right, now here's another point that many people are confused about. So in this axis, so what is the acceleration due to gravity? It's a vector pointing in this direction, right? And the magnitude of this is g. We write this as the magnitude as g. Let me write it in vector form. It's 0I minus gj. You guys understand? All right. Let's say I choose to draw my axis like this. Which way is the acceleration due to gravity? Okay, can you tell me the components of? Go ahead.
G, I, and 0 J.
Okay, be careful. Minus gi. You got the important part right. Okay. Anybody?
0 I minus 10K.
Okay, so you guys understand the acceleration vector always is pointing down, and its component will depend on your choice of axis. Okay, you like to make life hard for yourself, you can choose this kind of axis. Okay, and A will be AXI plus AY. Okay, so let's say this is theta. This will be G cosine theta I plus G sine theta J. Okay? All right. Of course, we don't like to do that. Okay. All right. So that finishes the lecture on this chapter. Okay. I see a lot of dazed looks, but maybe you're just tired and don't have coffee, unlike me. Okay. So what we'll do is you'll get a 5